I'll begin with a word of prayer. Heavenly Father, we thank you again for the weekend, and it's time to relax and refresh. Just pray that you be with us today. Help us to, again, Lord, glorify you in what we do, and just learn a little bit more about your creation, Lord. In my prayer, Lord Jesus. Amen. So you guys have any questions in particular? I mean, no is okay, but if there are, I take one. Let's see here. So there's no questions then? All right.
Just give me a reminder, how do we find the nth derivative of a function?
How do we find the nth derivative of a function? Without what?
Without calculating.
Oh, okay, yes. Let's see here, an example of that. So the kind of sneaky Taylor's theorem calculation. So if I had something like, I don't know, so as I had, let's see here, x squared plus 3x cubed, all right, times the sine of x minus 1, all right? Let this thing be equal to f of x. I could say calculate which derivative do you guys want? Let's say the 31st derivative at 0. So obviously I don't want to differentiate this thing 31 times, right? I mean, maybe you do, I personally don't. So what I need to do, right, is I need to find the Maclaurin series for this function. I need to expand this function as a power series in x. Now it's kind of halfway there in some regard, right? This part's fine, but the sine, there I should use the adding angles formula for sine, right? So that's sine of x times the cosine of 1 minus the sine of 1 times the cosine of x. Now the reason I do that is because if I do that, then it's very easy to rewrite this as power series in x, because I already know the Maclaurin expansions for sine and cosine, right? So without further ado, I can rewrite this as x squared plus 3x cubed, right, times the cosine of 1 times the sum, let's say m equals 0 to infinity, of minus 1 to the m over 2m plus 1 factorial times x to the power 2m plus 1, and then minus, what's the cosine is all times that, minus the sine of 1 times the sum, let's say j equals 0 to infinity, minus 1 to the power j over 2j quantity factorial, x to the power 2j, close parentheses. And so, right. So this is equal to, right? If you think about it, I mean, I can keep going down this path, but for me, this is far enough to think about it, all right? I can think about multiplying these out, right? You can think about multiplying these out, and you get something like C0 plus C1x plus C2x squared plus dot, 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 plus, you know, the kth component, x to the power k, right, plus dot, 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 dot. And then what does Taylor's theorem say? ck is what? Ck is equal to the kth derivative at 0 divided by k factorial, right? So my point is, I can calculate these constants, these coefficients, C0, C1, C2, and so forth. It's just a matter of multiplying out the series, right? When I do that, the meaning of the coefficients is that they tell me the derivatives of the function at 0 divided by k factorial. So if my goal then is to calculate, right, basically, so the 31st derivative at 0 would be equal to 31 factorial times C31, right? How do I find C31? Here, I'll do some easy ones for you. 0, 0, right? Because it's x squared. Now, this thing, right, is at least x. And this thing is minus sine of 1 is the lowest. It might even be instructive for me to write out this step here again, a little bit more detail. X squared plus 3x cubed. You know, I could rewrite this. This is cosine of 1 times x minus 1/6 x cubed plus stuff, right? Minus the sine of 1 times 1 minus 1/2 x squared plus da-da-da. Those are the Maclaurin expansions for sine and cosine respective. So from that, it's pretty easy to read off that the squared coefficient only comes from, like what? This guy times this guy, basically, right? So C2 is what? C2 is minus the sine of 1, which incidentally would tell me that f prime prime of 0 is equal to minus 2 sine of 1, because 2 factorial is 2, right? To find the third derivative, what would C3 be? How can I get cube? To get a cube, I can take this x squared, right, times that x. That's one way I can get a cube. So that gives me a cosine of 1. Anything else? How about this x cubed times this minus sine 1? So minus sine 1, you know? Is there any other way to get a third power of x as you multiply those power series out? I don't think so, right? I mean, everything else is higher powers if you look at it, right? So this tells me then the third derivative at 0 is equal to 3 times the cosine of 1 minus the sine of 1. Oops, I can't do math. What's 3 factorial? 6. So 6 times that. So there's the second derivative. There's the third derivative. The first derivative is 0. The function evaluated at 0 is 0. All right, so I think we've done enough that we can figure out what the 31st one is, right? So you got to think about how can you get a 31st power from this? How can I get a 31st power? How about x squared times what? Well, x squared times this piece is no good because that's an even power, right? I'm looking for a 31st power, so it's not this. It's just coming from this. So C31 is equal to the cosine of 1. And how do I get, what do I need here? If this is square, I'm trying to get 31, I need this to be 29, right? I need the exponent there to be 29. How do you get 29? You put m equal to, what's that? 14, right? So minus 1 to the 14 is plus, and that's a 20, so it's basically a cosine of 29, a cosine of 1 over 29 factorial. That's what I get from multiplying the x squared times this stuff, cosine 1 out here. And then minus the sine of 1. Let's see here. I've got an x cubed. Oh, there's a 3, right? Did I account for that 3? I think I might have missed this 3 here in my previous talk. Where did I miss this 3? Where should have that been? let's see here, to get the third power, it should have been here, right? That should have been there, because there's this 3 times sine 1, right guys? Oops, sorry about that. So 3 times sine 1, there's a minus here, and then I'm looking for a net power of 31, right? So if this is 3 of them, then 31 minus 3 is 28. I need this to work out to x to the 28, right? So that puts us j equal to 14 again, I guess, right? That's an accident. It doesn't have to work out like that, right? If I had an x to the 5th here instead of an x cubed, it would have worked out differently, right? So anyway, minus 1 to the 14 plus, and then so that's divided by 28 factorial. So that tells me then that the 31st derivative at 0, right, is equal to 31 factorial times cosine of 1 over 29 factorial minus 3 times the sine of 1 over 28 factorial. I think the problem I put in your homework is considerably simpler than this, but these are the ideas, right? Any questions?
Would our process change at all if we were still trying to calculate f31 at 5? You know,
Oh yeah, if we were trying to calculate the 31st derivative at 5, that's a much nastier problem. To do that, to calculate the 31st, right, 31st derivative at 5, I would do something personally like this. I would do x minus 5 plus 5 quantity squared plus 3 times x minus 5 plus 5 quantity cubed. All right? And then I would rewrite that as the sine. Let's see here. X minus 1 is equal to what? X minus 1 is equal to x minus 5 plus 4, right? So I would trade sine of x minus 1 for sine of x minus 5, cosine for plus the cosine of x minus 5, the sine of 4. And then I would expand this stuff out, right? Like this is a x minus 5 quantity squared plus, I want to say 10 times x minus 5 plus 25. And when you multiply the second one out, it's more complicated, but you know, this is going to go to like 3 times x minus 5 cubed plus some stuff. I'm going to make a mistake if I try to do it on the fly. 125, I mean, I'm not going to work it out. But the point is you have just powers of x minus 5, then you can multiply it out. Or you can think about, I wouldn't actually multiply it out, I'd think about multiplying it out, and I'd collect possible ways to get x minus 5. See, because the f of x can also be written as the sum, let's say n equals 0 to infinity of the nth derivative at 5 over n factorial times x minus 5. I mean, there's nothing particularly special about 0. You can write Taylor's theorem centered at any point. But if you center it at 5, then you're obligated to change all the x's to like x minus 5s by some sneakiness. Here, let me do this for a less complicated problem. All right, it's an important question. Ooh, that marker doesn't really erase. Yeah, fine. I think it's time to wash my shirt. Let's see here. All right, so for example, if I had something like, f of x equals to 1 over 3 minus x, we could write this different ways, different places, right? Like, so first of all, if I want to express this as a power series of 0, I just factor out the 3, right? And so the Maclaurin series, 1/3, sum, n equals 0 to infinity, x over 3 to the power n. Cleaning it up a bit, this is the sum, n equals 0 to infinity of, 1 over 3 to the n plus 1, x to the power n, right? Where is that series expansion good for? That's for the radius, the modulus of the radius, which is going to be absolute value of the radius, x over 3 less than 1, aka the absolute value of x less than 3. In other words, this has the interval of convergence of minus 3 to 3, right? Not included because this is geometric, it loses the endpoints, both of them, all right? Now, what if I want to expand at some other point? Say I wanted to expand at x equals to 1. How would that be different? Well, here's how I would do it. I mean, there's various ways you could do it. You could directly apply Taylor's theorem and just calculate derivatives until you see a pattern. I can't stand to do that because I like to think this way. So I just imagine, basically I want to change x to x minus 1, right? How do you do that? You add and subtract 1. That's the trick. I mean, that's my trick anyway, but not just my trick, but it's a trick. So this is 3 minus x minus 1 plus 1. All right, I'm going to put some parentheses around my trick. Now rewrite that a little bit. This is 1 over, how does that go? 2, right? Minus parentheses x minus 1. Just to check, you can easily see that if you distribute this minus out, you get back to 3 minus x, right? And the reason I do that is very simple, because if I do that, then I can find the expansion of this function about 1 without a lot of work, right? So this is a standard trick I'm showing you. Let's see here. So this is 1 over 2 times 1 minus x minus 1 over 2, right? The reason I do that is because then this is geometric. So this is 1/2 sum x minus 1 over quantity 2 to the n power n equals 0 to infinity, and then cleaning it up. See, this as it stands is not a power series. It's not a power series until you rewrite it in the form coefficient, right? In this case, 1 over 2 to the n plus 1, and then x minus the center raised to a power. Okay. Now, of course, you could find the coefficients here by direct differentiation if you wanted. This one's not that complicated, but this method I'm showing you easily addresses problems where I have, like, x cubed up here or something annoying. You can do almost the same trick. Well, that one's just a little bit ugly, but all right. Anyway, enough about this. Just a friendly reminder. This is some things that you may or may not have seen in calculus too. It kind of depends on your instructor and how they approach things. But okay, so yep.
Just one more quick one.
Mm-hmm.
Number 2. Can we use this?
Number 2 on which section?
12, I should say. That's not one.
Which section though?
On the mission, the one you gave us.
I don't have that in front of me. You'll have to explain. Sorry.
Find the power series expansion of block. And can we assume, do we use this sort of form for it?
Yeah,
And just
yeah.
say it doesn't converge over some interval?
Well, I mean, this of course is legit for what? This is for absolute value of x minus 1 over 2 less than 1. That's when the geometric series result holds for the radius being, the ratio being less than 1 in absolute value, which is to say x minus 1 is less than 2. Of course, none of this is terribly surprising. This function has a vertical asymptote at x equals to 3, right? And if I wanted to plot it, what's it look like? It's, let's see here, if I just figure out one point, I can figure out the rest. If I plug in 0, I've got a third, right? So it looks like this. That's this function. And so if we use 0 as the center point, right, we're getting this sort of convergence, interval of convergence like that, right? Basically, 3 is where it bumps up against. You can't go past that. So that's why our power series works from minus 3 to 3 when we center it around 0. In contrast, when we center it at 1, right, then what happens is we get this, which is what? The distance from 1 is 2, right? So that's exactly this to that, right? This is the interval minus 1 to 3. That's the interval of convergence for the series. So they're both running up against that natural singularity in the function that you can't get past, So yeah, I think the problem that you're talking about, Luke, we can do pretty much by the same methods that I'm doing. That x squared is a little bit annoying. So you'll actually have to add series and combine terms and stuff. It's a little bit more complicated, but yeah. All right, so let's talk about, so I think I've shown you guys, I could sit here and spend another hour looking at a differential equation, supposing that the form of the solution is a series, plugging it in and doing the recursion, right? We could do that for another 3 hours of class, and it wouldn't help you learn the method anymore. You just go back to the last class and look at what we did there. That's it. That's the method. There's really not much more than that. There's some things in the book about initial values. If you have an initial value, you can build the initial values into the coefficients in a certain way. But, ignoring the initial value issue, what we did last time is pretty much the method. You go from, it's kind of an odd situation, right? On this first test, you had this this army of techniques, right? All these different strategies and methods for solving different kinds of problems, and they're all nuanced. They're very nuanced. What you do in this case, in that case, and there's this annihilator method and all this other stuff, right? But then the series technique. What's the technique? You assume it's a series, and you plug it in, and that's it, pretty much. So it's kind of, but I guess the devil's in the details, isn't it? That sounds simple enough, but the actual implementation of that for specific problems is rather daunting, isn't it? But I think most of the homework that I've assigned you guys for Wednesday it's not actually that. There's like 2 or 3 of those in there, but mostly it's just skill building for power series and the ideas. So I wouldn't assume that it's a homework you can't do before Wednesday. I'd assume you can do a lot of it before Wednesday. There's only a couple problems in there that are really difficult. Maybe one. I don't know if it's really that difficult. It's debatable. All right, so let's talk about, excuse me, the method of Frobenius. All right. All right, so let me state the problem. Basically, we're looking at how to solve y prime prime plus p of x times y prime plus q of x times y equals to 0. Now, that's not a, I haven't really explained it to you yet. Before this, right, you could think of it as x squared y prime prime plus, how's it go? Oh, language. Fine, he puts an ax squared plus bx plus c. Ax squared, goodness gracious. Oh, come on, this marker. Ax squared plus bx y prime plus cy equals to 0. All right. So that for a, b, and c constants is what? That's the Cauchy-Euler problem, right? We already solved that previously, right? Remember that? We looked at solutions y equals x to the r. We found, and then there was weird stuff, right? There's like square roots in the solution set. There could be cosines of logs in the imaginary. There's all kinds of weird stuff in there. So basically what we want to do is look at the Cauchy-Euler problem, but now we're letting a, b, and c not be constants anymore. We're taking a, b, and c and we're saying a, b, c functions of x. All right. And in fact, for convenience, we're just going to let a be 1, just to make things a little bit easier to think about. All right. So what would the relation be between? What would the relation be between, like, the b and the p and the q? So if I was to take x squared, I'll just work it out here. X squared y prime prime plus, bx y prime plus cy equals to 0. If I take this and I divide by x squared, right, I get y prime prime plus b over x y prime plus, what's it go here, c over x squared y equals to 0. And of course this is for what? For x not equal to 0, I make that step. So if you want to translate between these two worlds, what's the relation between the p and the q and the b and the c? Like our p, right, is p of x is basically equal to b of x over x, or if you like to strip off the x's here and just write functions, p is equal to b over x, so to speak, all right? And q of x is what? Well, q of x is equal to, c of x over x squared, or if you want to, be a little bit more lean in the notation, we could write that as c over x squared. Okay. These are evaluation of the function at x. These are not multiplication by x, okay? Now here we're assuming that these a, b, c functions of x, we're actually going to assume that these are analytic functions. And we're going to do everything at 0. It's just, we work the method out at 0, and then at the end of it, we're like, okay, you can shift it to another point. It's just too much trouble to try to explain the method at a point other than 0. In fact, I've already been doing that with power series, right? I did power series at 0, but you could work out a problem that was centered somewhere else, right? It's just a hassle. And because they don't pay me enough, I don't do those problems. So, that's not entirely true. It's just I don't want to overwhelm you guys with... the problem is complicated enough without cluttering it by centering it somewhere other than 0. All right. So, these are analytic, analytic functions. Okay? So what does that mean, analytic functions? right? So to say that B and C are analytic functions, we have B equals to what? Something like, B naught plus B1x plus B2x squared plus B3x cubed, and so forth, right? We can expand it as a power series. That's what it means for it to be analytic at 0. The function is well approximated by its power series. Likewise, C is equal to C naught plus C1x plus C2x squared plus C3x cubed, so forth and so on, right? So what are the quote-unquote power series? What are the series expansions for P's and for the P and Q's? What do those look like? Well, P is equal to B over X. So what happens? We got B naught over X, right? Plus, well, as it happens, B1, right? Plus B2X plus B3X squared plus dot 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 dot. So after we divide the differential equation by x squared, the coefficients are actually no longer analytic functions. There's something else entirely. Look at that. This is not a power series. See that 1 over x? What happens to that at 0? Yeah, that goes to infinity. This function is singular. It's got a singularity. It's not analytic at 0, right? How about Q? Well, Q is C over x squared, right? Which is, by the way, C naught over x squared plus C1 over x plus C2 plus C3x plus dot dot dot. So P and Q are not analytic at 0. They have singular points. 0 is a singular point. Some language for this. This means that P has simple pole at 0. And this is what this shows you is that Q has pole of order 2 at 0. A simple pole is a pole of order 1. Right? Did I ever tell you the joke? So there's a Russian theoretical physicist and a rabbi and a Polish janitor on a plane, and they're flying, and then the pilot has a heart attack, and then they're like, who should fly the plane? And then the Russian's like, I'm a theoretical physicist. I don't know how to fly a plane. I only know how to do equations. And then the rabbi's like, I'm sorry, it's Saturday. Oh well. And then, of course, the Polish janitor goes, but I'm just a simple pole in a complex plane. Okay, sorry. So I usually can only work that into complex variables, but I found by using the term simple pole here, it gave me license to make this joke. So I'm pretty happy about that. All right, so this is a new math thing that you're seeing here, this notion of a pole, right? There are things that are worse than this. This thing, e to the minus 1 over x squared, that's actually what I should have had. I had a 1 over x in the previous lecture. That was supposed to be minus 1 over x squared. When I showed you the example function, which was smooth but not analytic. This thing, if you expand the power series, it's 1 minus 1 over x squared plus 1 half 1 over x to the 4th minus 1 over 6, 1 over x to the 6th, and so forth and so on. This is what's called an essential singularity at 0. When you study complex analysis, you find out all kinds of weird things about essential singularities. They have very unpleasant behavior. Simple pole and a pole of order 2, these are relatively manageable. Yeah.
And essential singularity is that because it has another pole, or because everything is separate.
It's because there are, if you look at, this is what's called the Laurent expansion, so like a power series with reciprocal terms, it's called a quote-unquote Laurent series. And so this is a Laurent series with arbitrarily high negative reciprocal power, negative powers in the denominator. Positive powers in the denominator, reciprocal powers of x without n is an essential singularity. This, on the other hand, just has 2. It just has 1. Okay, so this is the kind of problem we're looking at because we're starting with a twist on the Cauchy-Euler problem, all right, which leads us to this thing. And in order for that to be a legitimate one of these, the coefficient functions, the p and the q, have to have this form, all right? For p and q to have this form, it makes this differential equation. Let me give it a name. It's called a star. And let me just abstract this a bit. So we say star has a regular singularity at 0. It's a regular singular point, all right? Provided what? So this is definition. Star has so-called regular singular point at x equals to 0, provided. So we need some conditions. Can you guys think of how can I like, what's a formula that captures p having this form, but without writing all that? I mean, there's a simple way to do that, provided the limit as x goes to 0 of x times p of x is equal to 0, and the limit as x goes to 0 of x squared times q of x is equal to 0. It's been a while since I wrote this. Let me see if I'm missing any. This is definition 3 on page 462 of your book. Singular point x naught is said to be regular singular point if both x minus x naught times p of x and x minus x naught squared times q of x are analytic at x naught. Oh, fine. I guess I've said it wrong. I've made it too complicated. You do need these conditions. It's true. But more to a better way of saying it is that x times p and x squared times q are analytic at x equals to 0. Okay, and you can replace x equal to 0 with another point if you wanted to. That would be, then you would want x minus x naught times p of x and x minus x naught squared times q of x to be analytic at x equals to x naught. So this would make x equals to x naught regular singular point of star if you had that. Again, that's huge because if they're regular singular points, that means we can expand the p and the q as not power series, but these Laurent series. And the good news is the Laurent series allow term-by-term manipulation much the same way power series do. So we can still do our make a guess, have a certain form, and plug it in and see how it works. That still gels. Now, before I get to the method, though, I need to talk more about regular singular points. There's some nice, easy, sort of low-level problems here to appreciate. You know, this Frobenius method is not, I mean, everything, most of what we do in here is real. We're solving a real second-order differential equation, but this method actually comes from the study of complex differential equations in the plane, in the complex plane. And so some of the terminology is still based on that. Like you talk about the radius of convergence. What do you mean radius of convergence? Well, a power series in the complex plane converges on a disk, right? So it literally is a radius of convergence. And so there's basically a theorem. The theorem says this. If star has regular singular point, then method of Frobenius, singular point, let's say x naught, right? Of Frobenius provides solutions on, you got two choices basically, either x naught not included to infinity, or minus infinity not included to x naught. So that's the nature of the Frobenius solutions. You've actually already, I mean, by the way, you could, for example, if I had, let's see here, how can we get square root of x from a Cauchy-Euler problem? I'm trying to remember. I want like y prime prime, x squared y prime prime, plus something. You know, let's pick a b and pick a c. I want my r times r minus 1 plus b times r plus c equals to 0. I want this to have 1/2 as a solution. How do I get that? Come on, guys. This is reverse engineering. It's an important skill. Oh, that's a good idea. So 1/2 times minus 1/2 plus, let's put b equal to 1. See if we can make it work. 1/2, which is plus c, so therefore c equals 2. We got minus, this is 0 equals 0, right? So if I choose c equals to minus, what is it, minus 3/4, that should do it. So if you look at y prime prime, x squared y prime prime plus xy prime minus 3/4 y equals to 0, then you got two solutions from this. You got y equals to the square root of x, but you know what? You've also got y equals to minus the square root of minus x. This is for 0 to infinity, and this is for minus infinity to 0. Is that right? Aw, stink. I can't do math. Okay, fixed. My point is, this differential equation, right, has a regular singular point at 0. The Cauchy-Euler problem is the quintessential regular singular point. Like x squared times q is x squared in this case. Excuse me. Take that back. Sorry, I'm having a brain not working. So let's see here. What would p and q be? I guess I have to divide, right? Divide by x squared. What's the p? So y prime prime plus 1 over x y prime, right? Minus 1 over 4x squared times y equals to 0. So my, if you look at this, this tells me px equals to 1 and qx squared equals to minus 1/4. So the Cauchy-Euler problem is the one for which p times x and q times x squared, these are just constants. Of course, they're analytic at 0, right? But it is a singular point. And that's why the solution set looks totally different than the other problems we've worked, right? Like the constant coefficient problems. And as you can see, that's the nature of the solution, right? 0 to infinity or minus infinity to 0. I mean, we didn't do this much, right? We worked with positive x just to keep it not so annoying, but there it is. So that's one theorem. The method we're going to look at will give us solutions from the singular point out to infinity one way or the other. I typically focus just on this case because if you understand this case, you can put minuses in places and get the other, all right? The other theorem, which is which is very important, is that if star has an ordinary point, what's an ordinary point? Then the method of plug in series, okay, plug in the power series, all right, like we did last time, that method provides analytic solution which extends to nearest singularity. There's lots of interesting and simple homework problems I can ask about too. To actually implement the method of Frobenius is involved. I'm not sure we're going to get to it today. I mean, I'll start it, but I probably won't. I definitely don't have time to solve a problem by the method of Frobenius today. My goal today is just to try to get you to understand what a singular point is and these theorems, all right? Okay, so what's this 2 mean? Let me show you an example. If we have x squared plus 1, all right, y prime prime, plus e to the x, y prime plus y equals to 0. All right, and we're just looking at, by the way, this whole chapter is just on the second order problem. You know. Oh, the other thing I was thinking about saying today, but I didn't get into, was, do you guys know how to integrate using power series? A couple from your homework like that. What do? The integration problems, you shouldn't use the plug-in thing. You should just convert the integrands to power series and then just integrate. Like, that's the fastest way to do it. But whatever. Every so often I do an integration problem by supposing the solution has the form of a power series and then plugging it in. But after I'm done with that, I always regret it because I'm like, oh, I could have just converted the integrand to a power series and integrated term by term. That would have been easier, you know? Okay, anyway, I digress. This right here has singular points. Let me show you how. So, you know, intuitively speaking, what is a singular point? I define regular singular point for you, right? If these conditions are not met, if x times p and x squared times q are not analytic, then it's not even a regular singular point. It's what's called an irregular singular point. Irregular singular points are above our pay grade. We know that they're out there, but we can't really say much about them. There is a certain amount of series. There is some theory of differential equations which has been developed for irregular singular points of certain cut types. But you'll need to consult a deeper differential equations book than the one that you'll need to spend another $5 on a old edition of Cuttington and Levinson or something like that. Anyway, basically you need to consult a graduate DE's book. What it boils down to. I don't know about those things. Okay, so I mean, I know that they're there, but I don't know how to do them. So we just talk about regular singular points in here, and we study irregular singular points, you know, from afar, like this. Okay, so here we go. Now I have. Oh, I'm an idiot. Nah. I divided the differential equation by x squared plus 1, But I seem to have forgotten that x squared plus 1 over x squared plus 1 is equal to? Yeah, 1, thank you. Okay, now, we have to think in complex domain, all right? So this number 2, this nearest, is in the sense of the complex plane. So you locate the singularities in the complex plane. All right? So x squared plus 1, when is it 0? Never. It's the sum of it's the sum of squares, right? But that's real. So I can't be real with you guys. We have to think more deeply. X squared plus 1, of course, is what? This is x plus I times x minus I, right? So the point is, we have division by factors of x plus I or x minus I in these, all right? So basically the coefficient functions p equals to e to the x over x squared plus 1, and q equals to 1 over x squared plus 1 are singular at plus or minus I. So if I want to think about the possible, a solution to this differential equation and how far the solution will extend, what's the structure of its convergence, let me give it a name. Well, we can do that now if you believe the theorem. Item 2 in particular. So I draw a picture. It's really not complicated, but anyway, I'm just going to leave it. It's really not that complicated. So here's I, and here's minus I in the complex plane, right? Imaginary axis up, real axis over. And then you guys pick where do you want to find a solution. See, this star has ordinary points where? What's an ordinary point for this differential equation? I mean, there are no real singularities to the coefficient functions. Okay? I mean, P and Q are everywhere analytic in the real sense. It's just the existence of these complex singularities that are cramping our style in terms of how far the solution extends analytically. So if you pick, you pick whatever center point. Let's start with 0. If I look for a solution to star, right? In other words, y equals to c0 plus c1x plus c2x squared plus dot dot dot, right? I plug it into star. I find the coefficients. How far will that solve? How far will that provide a general solution to star? The answer is as far as the disk in the complex plane can extend before it hits singularity. So you just imagine a circle growing out of your center, and when it hits the nearest singularity, game over. So this will be solution for minus 1 to 1. Because this distance is 1, right? This distance is 1, so that distance is 1. Now I do not know, without further analysis, if 1 or minus 1 are actually going to be included in the solution set. The edge of the disk is up for grabs, always. It's not like those geometric series problems we did earlier today where we had knowledge from the kth term test and the structure of the geometric series that we lose endpoints. That's not the case here. It's more. So you guys pick another point. Like what if we looked at a solution centered out here? If we looked at y equals to c naught, let me say b naught plus b1, and let's say that point is what, 2? That's good. So b1 times x minus 2 plus b2 times x minus 2 squared, and so forth, all right? So a power series solution centered at the ordinary point 2. Item 2 in this theorem says that solution exists and it works for us right up until the the disk centered at 2 in the complex plane bumps up against the nearest singularity. So can you see where that happens? So if you imagine it happens to hit both of the singularities at the same time because of the shape of this, right? But it's bad, but okay. So that's a circle of radius, whatever this is, right? What's the radius? This is a triangle, right? 1, 2. R is the square root of 1 squared plus 2 squared, right? Which is square root of 5. So this will be solution 2 minus root 5 to 2 plus root 5. Square root of 5 either side of the center point. That's what the theorem tells us. Mm-hmm.
Could we, just doing 1 and 2, could we do a -1 plus I? Would that make any sense in this context?
You want to look at a solution centered at -1 plus I?
Yeah. Is that more we were talking about something?
-1 plus I, the solution over here. So that would be something like z, well, w equals, I don't know, a naught plus a1 times z minus 1, well, plus 1 minus I plus dot 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 dot. Yeah, that would solve the differential equation on this disk. It would only possibly impact. It would only give you a possibly real solution at one point. Anyway, no, this is outside the realm of the course. This question is forbidden. But in fact, the method is general. I mean, we can solve complex differential equations by much the same method. We don't have a course in that. We don't get to that in complex analysis. Doesn't assume differential equations, right? So like this is way in the weeds for the complex analysis course because we don't do differential equations there, right? But this is too much of a complex analysis thing you're talking about to do in here. So it's just, oh well. Fortunately, not so much needed for applications. It's probably not true. There's probably an application that needs it. But anyway, how about this? Another example. If I had x times x squared plus 4x plus 5, y prime prime plus 1 over x minus 2, y prime plus y equals to 0. Right? It's kind of an awful thing. But you can, you can actually see it from this. So this will have singular points for, well, obviously x equals to 2 is a trouble, right? That's going to give us a place where this coefficient is not analytic after we divide by the leading coefficient. But even without dividing by the leading coefficient, you can see, and also wherever x times x squared plus 4x plus 5 is equal to 0, right? Now this is either going to give you x equals to 0 or x plus 2 quantity squared plus 1 equal to 0, aka x is equal to minus 2 plus or minus I. Those are other complex zeros. So in this case, we have 1, 2, 3, 4 singularities for this differential equation. Let me plot them. And you ought to be a little bit careful here, right? Because if your picture is not to scale, you could get into some trouble, right? Minus 2. That's usually the sort of thing I say right before I make a geometric error in my example. Let's see here. So here's minus 2 plus I. Here's minus 2 minus I. And where's my other singularity? 2. Think here.